Let's talk about connectivity. So connectivity is very important topic in graph theory. So we try to understand connectivity, in very in-depth way. First, I start with basics. So finally, what we are going to do is we are understanding here what is path, and what is connected graph, what is disconnected graph, and what are the properties of connected graph and disconnected graph. Okay, so that's the overall idea about connectivity. To understand that connectivity clearly, first we start with a formal definition called path. Okay, so what is path? Path is a simply sequence of edges, just sequence of edges. Example, see this one, 1 comma 2, 2 comma 3. What is the meaning of sequence is, if you take any edge in the path, okay, path is a collection of edges, I can say. So this is, let's say, one edge, right, 1 comma 2, and since it is ending with 2, the next edge should start with 2, then we say it's sequence. Okay, now 1 2 2 3 3 4, see, ending of one edge should be starting of another edge. In that way, if you form some collection of edges, so that is called sequence of edges. So path is collection of such sequence of edges. Okay, so we say that 1 is the starting vertex of that path, and here 3 is the ending vertex of the path. So we also represent this idea like this, so that it will be easy to understand. 1 2, so rather than set form, I can take this kind of picture, like this one, pictorial representation. 1 2 2, then 2 to 3, and this one 3 to 4, and next one starts with 4 and ends with 3. So I can write like this also, 1 2 3 4 3. Starting vertex is 1, ending vertex is 3. Number of edges in this path is 1 2 3 4, and this is a path. Okay, but what is not path is this one, 1 to 2 5 to 6. This is not a path because it should be sequence of edges. Okay, there is one interesting path, that is, trivial path. That means if I start at 1 but I don't take any number of edges, that means I take 0 edges, then still we say that is a path. So this is a path. Okay, so you are not seeing any path here, right? So you are just seeing a vertex. Yes, you can't see path clearly because there is no edge inside it. So this is called trivial path. Okay, trivial path. Trivial path is a path with 0 edges. Okay, then how to imagine this path, I will tell you. Let's say Raju is an imaginary student. Okay, Mr. Raju is starting at city 1, like he want to go from, let's say, city 1 is Hyderabad. Okay, so Raju want to go from Hyderabad to Hyderabad without any cost, like without any road. Then what he can do is, so he will start at Hyderabad, let's say 1, then he will close his eyes and he will open his eyes. That's it. Then he will be at Hyderabad. So that path is called trivial path. So every vertex, by starting at any vertex, always I can have a trivial path, right? So this is about trivial path. But don't get confused with loop. Example, if you have loop like this, that is different. Example, Raju starts at 5, and if he uses loop, then he will use one edge. Then pictorially we represent like this. This is not trivial path because this path contains one edge, right? So if there is any path without any edges, that is called trivial path. So that's why self loop is, if you take self loop in the path, that is not trivial path. Okay, so it's also non-trivial path. Now this is about paths. Let's come to simple path. What is simple path? So simple path is a path, what is path? Without repetition of edges. Okay, we should not repeat the edges. Example, here 1 to 2, 2 to 3, 3 to 4, 4 to 3. You see, 3 to 4, 4 to 3 is same edge, isn't it? So you have repeated an edge here. Then this is not a simple path. Let's draw one simple path here. Example, 1 to 2, then 2 to 5, 5 to 6, 6 to 3, 3 to 4, 4 to 1. This is a simple path, right? So here starting vertex equal to ending vertex. So what? Still the question is about, it should be a path. The definition says that we should not have repetition of edges, right? Are we repeating edges is the question. This is 1 to 2 edge, 2 to 5, 5 to 6, 6 to 3, 3 to 4, 4 to 1. No repetition of edges. Some students say that, sir, you are repeating here. I am repeating vertices, not edges, isn't it? Don't get confused between vertices and edges. Okay, that's why still this is a simple path. Okay, you can have a lot of such paths. Every trivial path, example, so 1 is a trivial path, isn't it, with 0 edges. This is a simple path because you are not repeating edges. Even you are not repeating edges, you don't have edges, then definitely every trivial path will become simple path. Okay, now let's see closed path. So closed path is a path, you know what is path, where start vertex equal to end vertex. So simple. Example, let's take this graph. 1 2 3 4 5 6. In this one, closed path is nothing but 1 to 2 and 2 to 3, 3 to 4, 4 to 1. Already we know that it's a path, and just observe starting vertex and ending vertex. Both are same, isn't it? That's why it's a closed path. One more example, 1 to 2, 2 to 1. Yes, I am repeating the edges. That's not an issue because in a path you can repeat the edges, isn't it? So in simple path you can't repeat the edges, but in general path we can repeat the edges, not an issue. And starting vertex equal to ending vertex. That's why these are all paths where starting vertex equal to ending vertex. So closed paths. Now open path. Open path is a path like any path where start vertex not equal to end vertex. That means starting and ending is different. Example, let's take 1 to 2, 2 to 3, 3 to 4, 4 to 1, which is closed path. Let me add one more edge, 1 to 2. See, this is not closed path. The reason, it's a path but where starting vertex not equal to ending vertex, isn't it? But for closed path, start should be equal to ending. That's why it is open path. I can say that open path is a path which is not closed. Okay. Now you understand what is open path, what is closed path. So in closed path, starting equal to ending, and in open path, starting not equal to ending. Now we'll see circuit. So let me read the definition of circuit. Circuit is a simple closed path. You know what is path? You know what is closed path? Where starting vertex equal to ending vertex. One extra condition is simple. So what is simple path? Simple path is a path without repetition of edges. Let's consolidate all of these things. One, it's a path where starting equal to ending, and simple means no repetition of edges. Any path without repetition of edges and which is closed is circuit. An example, let me take this one, 1 to 2, 2 to 3, 3 to 6, 6 to 5, 5 to 1 and 1 to 4 and 4 to, let's take 1 back. This is circuit or not? We'll see. First thing, let me check the definition. In definition, first it should be path. Yes, it is a path. Already I checked it. You also check it. Next, is it closed path? Yes, starting equal to ending. But is it simple? If it is simple, no repetition of edges. But you see here, 1 to 4, 4 to 1. I have repeated the edges. That's why it is not circuit. In that way, easily we can check whether a path is circuit or not, isn't it? Let's see one more example of graph. Let me take a graph 1 to 2, 2 to 3, 3 to 4 and 4 to 5, 5 to 6, 6 to 4. Let me put an edge here, here to here and here to here, here to here. So my question is, I'll give you a path and check whether it is simple closed path or not. Otherwise, is it circuit or not is a question. I'll give you a path. 5 to 1, okay, 5 to 1, 1 to 2 and 2 to 4 and 4 to 1 and 1 to 5, then 5 to 6 and 6 to 4, 4 to 5. I have given some path. Is it circuit is the question. We'll see. First step, it is really circuit, simple closed path. That means it should be closed path where starting should be equal to ending. Perfect. 5 equal to 5. Second one, what about simpleness? Is it a simple path? Then there should not be repetition of edges. Let me mark the edges in this graph so that I can check the repetition. 5 to 1. Yes, let me cover it. 1 to 2. Yes. 2 to 4. 2 to 4. Okay, this is covered. 4 to 1. Okay, 1 to 5. See, you have repeated 1 to 5 two times. That's why even that path is not circuit. Okay, one more example. Let's take 5 to 1, 1 to 4, 4 to 2, 2 to 3, 3 to 1, 1 to 6, 6 to 5. Is it a circuit? Is the next question. Stop the video here and think about it, whether it is circuit or not. Okay. After that, after solving this problem, again start the video. Okay. Start. 5, 1, 4, 2, 3, 1, 6, 5. Is it a simple path? We will see. For that, no repetition of edges. 5, 1, 1, 4, 4, 2, 2, 3, 3, 1, 1, 6, 6, 5. I don't see any repetition of edges. That's why it is a simple path. And is it closed? Yes, starting equal to ending. Okay, so that's why it is circuit. Simple closed path. In that way, you can understand about circuit. We'll see one more thing, which is cycle. So what is cycle? Cycle is a circuit. Okay, you know what is circuit. But extra condition, what is it? Where no repetition of vertices. We should not repeat the vertices. But without repetition of vertices, how can you form closed path? And why should we form closed path first of all? To form circuit, it should be closed path. But cycle says that its condition is circuit and where no repetition of vertices. Without repetition of vertices, how can you form the closed path? That's why the exception at the end you can repeat the vertices. At the end you can repeat, that's possible. Apart from that, you should not repeat the vertices. Okay, that's the exception. So finally, cycle is a circuit where no repetition of vertices except last vertex and first vertex. So example, is this path a cycle? If really it is a cycle, then what is the condition? First of all, it should be circuit. Yes, we know that it is circuit. And what is the extra condition? No repetition of vertices. Okay, don't check this one because without that we can't form a circuit. Apart from that, you can see the repetition of vertices here, isn't it? That's why it is not cycle. One more example I will show you. 5 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 6, 6 to 5. Is it a cycle? We'll check. Blindly follow the definition. What is the definition of cycle? First it should be circuit. What is circuit? Go to the definition of circuit. Simple closed path. Okay, first of all let me check whether it is circuit or not, then after that I will check whether it is cycle or not. Okay, so circuit, simple closed path, simple, no repetition of edges. 5 1 1 2 2 3 3 4 4 6 6 5, no repetition of edges. Okay, if you have any doubt, go to the graph and mark the edges. Based on that you can decide whether edges are repeated or not in the problem. Second one, yes, no repetition of edges. Is it closed? Yes, 5 and 5. Yes, simple closed path. So that's why this is circuit. But a circuit is cycle only if there is no repetition of vertices. So apart from these ends, are you seeing any repetition? No, right? That's why no repetition of vertices. It is a cycle. So these are all fundamental things in connectivity topic. Okay. So you learn what is path, what is simple path, what is closed path, what is open path, what is circuit, what is cycle, isn't it? So using that we are going to define connectivity.